Thanks everyone for coming. It's a great pleasure to have Ken Yagi with us today from the University of Virginia. He's a PhD at the University of Kyoto, and he was a postdoc at Montana State where I was a grad student, so I've worked with Ken quite a bit while working on my PhD. And he was a postdoc at Princeton and now a professor at the University of Virginia, and Ken's an expert on neutron stars and testing general relativity, so it's here.
Thank you very much, Katerina, for a nice introduction. Good afternoon, and thank you very much for the invitation. This is my first time in Toronto, and I'm having a fun stay so far. So today I'd like to explain a bit about what we can learn about the nature of extreme gravity using the recent discoveries of gravitational waves by the LIGO and Virgo collaboration. And I was told that you've been trained on gravitational wave physics and also the recent discoveries. So this is just one summary slide showing what we have learned so far from this historical discovery. In terms of astrophysics, we have learned that the mass of the stellar mass black holes inside the binary system that LIGO found was a few times larger than what people have found using, for example, X-rays. Like the very first event already had 30 mass and 35 solar mass. They collided to produce 62 solar mass. So that's very large compared to what people have found already using X-ray telescopes. And also the very recent event of neutron star binary merger, they confirmed, at least for this event, that the origin of short gamma ray burst is associated with two neutron stars colliding. So that's a huge discovery. In terms of nuclear physics, since this event, binary neutron star merger, gravitational wave event, did not detect the tidal effect, that means you can place upbound on the effect of tidal lab number or tidal deformability of an object, and they concluded that's what's called softer equilibrium states are more preferred rather than stiffer equilibrium states. Softer equilibrium states tend to produce more compact objects, so they are more difficult to get tidal deformed. So this is the implication that LIGO brought us on the nuclear physics side. In terms of cosmology, gravitational wave observation allows us to measure the luminosity distance of an object. And for this neutron star binary system case, since we had electromagnetic counterparts, we could identify the host galaxy. And since we already knew the redshift of the host galaxy from previous electromagnetic telescope observations, we could combine those information to measure the Hubble constant. And it turned out that LIGO's measurement of Hubble constant is consistent with what have been measured using a supernova and also CMB. And the error bar is still large, that they couldn't resolve the tension between supernova and CMB, but in future, as the detector sensitivity improves, we would expect to shrink the error bar so that maybe we have some implication on the tension between the two measurements. And finally, in terms of gravitational physics, these new gravitational wave sources allow us to probe strong and dynamical field regime of gravity for the first time ever. And this is the topic of my talk today. So let me briefly explain why do we care about testing GR. And there are several aspects, but obvious reasons are that from cosmology side, we could explain the missing mass of our universe and also accelerating expansion of the universe without having to introduce dark matter or dark energy. So that's the one motivation coming from cosmology side on considering gravitational theory away from GR, and also from particle physics or high energy physics side. If you want to quantize gravity, then it looks like you need to modify gravity from general relativity. For example, if you take string theory, then string theory is higher dimensional theory. So if you compactify the extra dimension, then you typically get scalar field like dilatons that couples to the metric field. And then if you take the low energy limit, that does not reduce to GR. That has some deviation away from GR. And the bonus one gets in studying gravitational theories away from GR is that you really appreciate how beautiful and simple general relativity is. And you might think that it's kind of too extreme to go beyond GR, since general relativity has been probed and then confirmed very accurately using observations. But at least in one point in our gravitational history, we had to abandon the theory that everybody believed and then move on to a new theory of gravity. And that happened in 19th century, where people found anomalous precession, perihelion precession of Mercury. And this could not be explained by Newtonian physics. So people predicted that there should be another planet. They named this Vulcan, whose orbit is inside the Mercury's orbit, and this Vulcan, hypothetical planet, is perturbing this Mercury's orbit, creating this anomalous perihelion precession. But of course, up until now, we haven't found such a planet, and then Einstein proposed his theory in 1915, and this general relativity beautifully explained this anomalous precession. So at this stage, people had to move away from Newtonian gravity to general relativity. So it may not be too extreme to consider moving away from general relativity. So that's why we need to keep testing and see whether general relativity is correct or not. And these gravitational wave events offer us very unique test beds compared to other existing systems. To see how unique these new gravitational wave events are, I'm going to show you on the horizontal axis the amount of gravitational potential for those systems that have been used to probe gravity. And on the vertical axis, I am going to show you the amount of curvature. The gravitational potential is essentially given by the ratio between the mass of the system that you are probing as compared to the size of its system. If it's a binary system, then this corresponds to how fast each object inside the binary system is moving with respect to speed of light. On the other hand, the vertical axis shows the curvature, which is given by certain combination of mass and the size of the system. And basically, in this plane, as you go to top right, you enter into stronger and stronger field regime of gravity, while if you're in bottom left, you are in weak field gravity regime. We know that solar system experiments using many satellites and also some lasers shooting towards moon and then reflecting back. That's called lunar laser ranging. By using those techniques, people have shown that general relativity has been confirmed to some very precise accuracy. But if you plot those systems, gravitational potential and curvature, then they are plotted by these green dots. And you can see that these satellites probe rather weak field regime of gravity. You can also use binary pulse observations to probe gravity, but the system themselves fall into not so strong gravity regime. They are quite similar to the solar system gravitational potential or curvature, but what's interesting about this system is that they consist of neutron stars, and neutron stars are very compact. So there are some observables in binary pulsar observations where you can extract some information about the strong field nature inside neutron star, and so that you can probe a very strong field nature of gravity. Now I'm going to plot in this plane gravitational wave events that LIGO and Virgo detected. And for example, the first event and second event looks like this. So notice first that they lie on this top right corner. So they are truly strong field sources. But moreover, they are drawn by lines instead of points. What does this mean? This means that within the observation period of 0.1 second to 1 second, these systems swept through all this range in this parameter space, which means that they are not only strong, but also highly dynamical. That's why they provide us very unique test beds compared to other systems which are rather stationary or static. And also, most of them lie in this weak field regime. So that's interesting. And also, in some sense, we can probe directly the nature of gravity because we are looking at gravitational waves directly, ripples of space-time directly, where all the other observations were done through electromagnetic wave observations like radio telescopes. So for the remaining of my talk, I would like to explain first what we have learned so far using black hole merger events from LIGO and Virgo discovery. And then I would like to explain what one can do in future if we can measure the ring down signal. And of course, LIGO and Virgo collaboration already detected the ring down mode of the first event, but we can do we can extract some interesting physics if we have better sensitivity. And since we now have events from neutron star binaries, I would like to explain what we have learned from this neutron star binary event using multi-messenger astronomy and what we can do in future. Unfortunately, this post-merger phase of neutron star binaries, it's quite messy, and we don't have accurate prediction even in GR, so it looks very difficult and challenging to use this phase to probe gravity, but maybe it's possible in future if we have astrophysical modeling under control. But for this talk, I would focus on these three parts, and I'll leave this for some other time. So first, the black hole binary in spiral part. What can we do? Especially, what can we learn in terms of gravitational nature? We can test various fundamental pillars in GR. For example, general relativity was established under 4-dimensional space-time, which means that you can look for tiny presence of tiny extra dimension hidden in the waveform. And if you don't find such an effect, then you can put upper bounds on the size of extra dimension. General relativity was also established under a very important principle called equivalence principle. There are many aspects, but one important aspect is this universal free fall, where the gravitational acceleration does not depend on the mass or the internal structure of two objects that are feeling gravitational field created by, for example, Earth. Alternatively, the gravitational strength, the gravitational force between two objects does not depend on the internal structure. That's what equivalence principle tells us. So we can check and see whether gravitational force depends on the internal structure. Like if you have the same mass, but let's say white dwarf and neutron star, then do they feel same gravitational force or different force? And that allows us to prove this equivalence principle. General relativity was also established under certain invariance, like Lorentz invariance, saying that there's no preferred direction in your space-time, so there's no vector degrees of freedom in general relativity. General relativity also predicts that gravitons are massless, so gravitational waves have to propagate at the speed of light, which we can test using the gravitational wave events and also the multi-messenger astronomy. Finally, we can look for additional polarization modes. And as you may know, general relativity only has 2 tensor degrees of freedom, like plus mode and cross mode. But in some theories of gravity, especially if you have some scalar field involved, then there could be some additional polarization where if you have rings of particles, then if the gravitational wave propagates orthogonal to this screen, then this ring of particles just shrink and expand in symmetric way. If you can find such additional polarization mode, then that would be strong smoking gun of non-GR effect. And this is something Katerina worked on a long time ago. So these are examples of some fundamental aspects in GR that you can look for. So in other words, you can look for violation of these effects hidden in the waveform. And if you don't find them, then you can place up bound on such violation effects. And to do such a test, what you need to prepare first is some template waveform going beyond GR. Because if you are using template that's created within GR, then you won't be able to find the signature of this deviation away from GR. So you need to prepare templates that can capture this deviation away from GR. And this is a schematic picture showing the waveform in general relativity in red and in certain modified theory of gravity in blue. And typically what you find is that you find deviation in the phase. So you need to capture this deviation in the phase. And there are several formalisms to capture this phase. But one example is this what's called parameterized post-Einsteinian formalism. The idea is quite simple. You take for the inspiral part of the waveform phase, you take the GR prediction, and then you just add one correction term that captures the information about non-GR effect. And this velocity V here is the relative velocity of two objects inside the binary system. This correction term has two parameters, beta and n. Beta tells you the overall magnitude of this correction term, non-GR effect. and this is called PPE parameter. Whereas this n in the exponent tells you at which post-Newtonian order this correction enters. And post-Newtonian approximation is valid whenever the velocity of the object is much smaller than the speed of light. For example, if this n is 0, then that means this correction term enters at the same order as the leading GR effect. And so here we are only keeping the leading post-Newtonian correction in the waveform. And what about the merger and ring down part of the waveform? Well, we did not include any correction, and that's because we currently lack enough number of simulations done in non-GR theories, so we don't really know how the waveform is modified in the merger and ring down part of the waveform that I do not show here. So to be conservative, we just keep the merger and ring down part of the waveform to be the same as GR prediction, and we just add correction in the in-spiral part and see if there's such a sign hidden in the signal. And ideally, we should use the actual data and use the data and compare the data against this template waveform, but we took a simpler approach where we inject a signal that's consistent with general relativity waveform with parameters that are reported by LIGO for, let's say, the first event. And then we try to recover this GR waveform using the template PPE modified waveform that can capture non-GR effect to see how accurately you can measure this PP parameter beta. And since we know that the injected signal is GR, this allows us to put upper bounds on the magnitude of this correction term. And I just show you the result. This is the upper bound placed on PP parameter beta as a function of at which post-Newtonian order the leading correction enters. The black dashed line is the bound obtained from double binary pulsar system, whereas the green crosses are the ones obtained by the LIGO and Virgo collaboration using full Bayesian analysis using actual data. Whereas our simplified analysis results are shown by these red points, and you can see that as an order magnitude estimate, this simplified Fisher bound is valid. And you can see that by comparing gravitational wave bounds against this black dashed binary pulsar bound, you can see that at least for this positive post-Newtonian correction side, gravitational wave events allow us to place stronger bounds compared to these binary pulse observations. And that's because positive post-Newtonian order corrections become larger and larger as you prove stronger and stronger field regime of gravity. And gravitational wave events have stronger field regime compared to binary pulsar systems. So that's why these gravitational wave events bounds are much stronger than the binary pulsar bounds. Great, but one must be careful when comparing these two different bounds, because just because you have stronger bounds on beta does not necessarily mean that you have stronger bounds on like certain theory you would like to place bounds on. And for example, there are some theories where you don't expect to see any modifications if you're looking at neutron stars, and you need to look for black holes to see deviation away from GR. And for those systems, you cannot apply these binary pulsar bounds. You have to use bounds obtained from a system that contains at least one black hole in it. So that's why it's important to obtain independent bounds coming from different sources. So that's why we wanted to extend this bound all the way down to negative post-Newtonian side, and which we did. And you can see that in this negative post-Newtonian side, gravitational wave bounds are much weaker compared to the binary pulsar bounds, and that's probably why LIGO and Virgo collaboration did not look at this negative post-Newtonian side, but still they bring us different pieces of information.
Okay, I'm a little confused about n equals 0. If I did the scaling right, n equals 0, that's the scaling would be equivalent to the binary separation you would get for the Newtonian phase shift over the in-spiral time. Because the in-spiral time goes as 8 to the 4th.
Okay.
And so the phase shift would be 8 to the 4th minus 3 halves, the Newtonian phase shift. So that would be 8 to the 5 halves.
Okay.
And e to the minus 5 is 8 to the 5 halves. So n equals 0, if I got it right, just corresponds to the, so for example, if you just consider n equals 0, then aren't you in essence just shifting the mass?
Yes, so there.
So don't you need an independent measure of the mass in order to claim that you can consider
Yes, when we do this parameter estimation, we not only include beta, but also mass and spins and so on. And then we do take into account the correlation between those parameters. So we are determining mass and also these PP parameters simultaneously.
But then following on though, well, I guess I don't quite understand why you're not just shifting the mass, but I understand how you go to negative n. How does that make sense?
For example, if you have the scalar field, then scalar field would activate scalar charge in, let's say, black hole. Then that would produce dipole.
The scaling of merger time.
Yes, it does. Yeah, it will make the merger happen earlier. And if you use a second event, then you get even stronger bounds on beta. So that's great. We now have bounds on these generic parameters. Now our task is to extract physics from this generic parameter. And the trick is by looking at different post-Newtonian order correction, you can gain different aspects of general relativity. For example, as I was explaining, if there's a scalar field, then scalar charge is activated on each black hole. That would produce scalar dipolar radiation. And since this is dipolar radiation, whereas gravitational wave is a quadrupolar radiation to the leading order, this enters at earlier post-Newtonian order compared to the gravitational wave 0pn effect. And then so this allows us to prove the equivalence principle, because if there are two scalarized objects, then there will be scalar force acting on each other. And this means that the gravitational force acting between these two objects depends on the internal structure of each object. So in that sense, you can check the equivalence principle violation by looking at this -1 pn order. And in the same manner, by looking at -4 post-Newtonian order, you can look for the presence of extra dimension, or you can check whether gravitational constant is actually constant or not. You can also look for the existence of the vector degrees of freedom in your gravity sector. If there's such an effect, that means you have preferred direction in your spacetime, which violates Lorentz invariance, and so on. So let's compare these gravitational wave bands to other bands that have already been extracted from solar system or binary pulse observations. And I'm going to give you a summary slide showing each example theory that will break at least one fundamental pillar in GR. And this column will show you the new gravitational wave bands obtained from the first event. The last column will show bands coming from other observations like solar system experiments. And the first class of example is shown here. You have example theories that violates, for example, equivalence principle or parity invariance. And I do not show any bound coming from the first gravitational wave events. And that's because the bound obtained from this system were too weak that it went beyond certain approximation that we use to derive correction in these theories. In other words, those bounds obtained from this event do not satisfy the approximation, so we could not obtain any meaningful bound in these types of theories. Whereas there are some theories where you can place up bounds on certain violation in Lorentz invariance or for dimensionality. And in this table, if numbers are smaller, that means you're placing stronger bounds. You are closer to GR prediction. And you can see that the numbers obtained from the first gravitational wave event is much larger compared to the numbers obtained from other observations, which means that these gravitational wave bounds are much weaker compared to other existing bounds, but they have meaning in the sense that these are the first bound obtained in the strong and dynamical field regime. And the interesting class is the third class, where you try to look for the deviation in graviton dispersion relation. So general relativity predicts that E squared is just P squared for the graviton's dispersion relation, but there could be some modification in this dispersion relation. For example, if you have massive graviton, then you have this additional term, which is just a constant corresponding to mass squared of the graviton. And there are many theories that predict violation of graviton's dispersion relation from general relativity prediction. And the important fact is that there are some parameter space in some series where you can place for the first time the bounds that could not be obtained from other observations. So regarding this violation away from GR encoded in the propagation, during the propagation stage of gravitational waves, you can actually place a very new bound on some parameter space in some theories. So you could obtain some new insights in terms of gravitational theory from this gravitational wave event. But the important message here is that the true potential of gravitational wave events is currently limited by a lack of knowledge of what's going to happen in the marginal phase if you go away from GR. So once you have lots of binary marginal simulations done in non-GR theories and you know how to modify the waveform away from GR, including the marginal and ring down phase, then you should be able to place even stronger bounds in future. And regarding other types of tests that have been done by LIGO and Virgo collaboration, for example, they have calculated the residual SNR, which is you take the data and you subtract the best fit template from the data, and you can calculate the residual SNR, and from there they concluded that the GR prediction for the first event is verified within 4% error. So this is a model independent way of testing GR. Another way of testing consistency of general relativity is to treat the in-spiral and post-in-spiral separately or independently, and then you can check for the consistency between the two. And they have also looked for additional polarization modes, and they concluded that the purely tensor polarizations are more favored than purely scalar polarization or purely vector polarizations. So these are the current status of what we have learned so far in terms of gravitational theory from the already existing gravitational wave events. And now I'm moving on to what we can do in future if we can measure binary ring down part of the waveform very accurately. So what you can do using the ring down part of the waveform is you can check the black hole no hair property, stating that astrophysical black holes only have two hairs, mass and spin, which means that this ring down part of the waveform is characterized mainly by two parameters, the ring down frequency and the damping time of this ring down mode. So if general relativity is correct and if the remnant black hole is curved black hole, then these frequency and damping time should only depend on mass and spin, which means that if you can measure this frequency and damping time of, let's say, the dominant mode, then you can take this mass and spin parameter space of the remnant black hole, and you can draw a curve corresponding to the measured frequency and damping time. And then you take this crossing point, and this will give you the mass and spin of the final remnant. On top of this, if you have additional information coming from higher order mode, then you can now start to check the consistency of curved black hole in general relativity. If general relativity is correct and if the remnant is a curved black hole, that means the third curve should also cross at exactly the same point as other two curves. And this way of consistency test of general relativity is same as what people have used for binary pulsar observations. There are what's called parameterized post-Keplerian observables, which depend on two masses of neutron stars in these binary systems. So you can take any two of these PPK parameters and draw the measured values with some error bars in this mass-mass plane, and the crossing point will give you two masses. And if you have third measurement, then you can start to check for the consistency of general relativity. So to do this kind of consistency test using ring down waveform, then what is crucial is to look for this higher order ring down mode. So the question is, do we have a hope of detecting such higher order ring down mode with advanced LIGO's, let's say, design sensitivity? This is the spectrum, gravitational wave spectrum for the first event with the dominant mode in green in spiral, merger, and ring down. And the blue curve shows advanced LIGO's design sensitivity noise curve. And roughly speaking, the ratio between the spectrum and the noise curve will give you signal to noise ratio. In theory, if general relativity is correct, then for this system, there should be next to leading order mode, and that's L equals 3 and M equals 3 ring down mode, whose spectrum should look like this red spectrum. If you take the ratio between red and blue, then you will find that the SNR, expected signal to noise ratio, is only like 1. And if the threshold is, let's say, 5, then it is very difficult, even for advanced LIGO design sensitivity, to measure such high order ring down mode. So people will say that, okay, we have to wait for third generation detectors where we have 10 times better sensitivity. But we will expect to see lots of binary signals in future. We already have 4 or 5. So what happens if we can combine those multiple signals together? That should enhance our signal to noise ratio. So can we detect this higher order ring down signal by stacking or combining multiple events? And let's say you have 15 identical events, then you can enhance your signal by 15 times larger. But if you stack those signals, you will also enhance your noise sensitivity level, but this will only increase by square root of the number of events that you combine together. So in the end, what you get is an enhancement in square root n of the original signal to noise ratio. So if you have 15 events, that means you have roughly 4 times better 4 times improvement in your signal to noise ratio, and now the signal to noise ratio for the stacked combined event becomes 5. So there is a chance of detecting such higher order ring down mode if you can combine multiple signals. But in reality, you don't have identical events. Each event will have different masses and spins and so on. So what can we do to combine those different signals coming from different sources? And if you have different sources, then of course they would produce different types of ring down modes. And they are not in phase. They don't have same phase. So if you just add them together, then you will have partial cancellation between these signals, and you won't maximize the information available. So what you need to do beforehand is to somehow align the waveform phase, something like this. So now you have everything with the same phase, and then you can now combine these signals together so that you won't have any cancellation going on. So the question here is how you can do this alignment of the phase. And to align this phase, what you need to know beforehand is the frequency of each mode in these signals. Because if you know what the frequency is, then you can rescale your time so that they have the same frequency. And to predict what the frequency of each signal is, what you can do is you can do consistency tests. Let's assume that general relativity is correct, and let's assume that we have measured dominant mode of the spectrum in spiral merger ring down of the dominant L equals 2 and M equals 2 mode. Then once from there you can extract the masses and spins of the events, and then you can assume GR is correct. So now you have a merger simulation prediction, and you can predict what would be the higher order ring down frequency is. And by using such information, you can try to align the phase of each signal. And to check whether this is doable or not, we carried out some Monte Carlo simulations to see the probability of detecting such higher order mode by comparing the case where you don't have any stacking to the case where you have stacking. And I've skipped the details and just show you the result. this plot shows the detection probability of measuring the higher order ring-down mode, assuming that advanced LIGO design sensitivity operates for 1 year as a function of the threshold SNR. And this blue histogram is the case where you don't have any stacking. Then if your threshold signal-to-noise ratio is 5, in this case, there is roughly 30% chance of detecting the higher order ring-down mode. Now, if you combine 15 loudest events available, then the detection probability improves significantly to this green one, and now the detection chance enhances to something like 98%. So now you have a better chance of detecting such high order ring-down mode by combining 15 events. And of course, there could be some more, like 30 or 40 events available. So we do have a good chance of detecting such high order ring-down mode if we can properly combine each signal together. So this was the what you can do in future using the binary black hole ring-down part of the waveform. And now I'll explain what you can do in future with neutron star binary in spiral. And already by using the new event detected by LIGO and Virgo collaboration, they carried out a few different types of tests of general relativity. And one important test was to measure the propagation speed of gravitational waves. General relativity, of course, predicts that the propagation speed should be same as speed of light. And for this particular event, people detected not only gravitational waves, but also photons, not only gravitons, but photons. And they know that the distance between us and the source is 40 megaparsec. And the arrival time difference of gravitons and gamma ray photons were 1.7 seconds. By using these two facts and by using some assumptions, some conservative assumptions, LIGO and Virgo collaboration concluded that the propagation speed of gravitational waves away from the speed of light should be constrained to a very high precision, like 10 to minus 15 to 10 to minus 16. This is a very stringent bound on propagation speed of gravitational waves, and this bound already allowed people to rule out many models in modified theories of gravity that can explain current accelerating expansion of the universe without introducing dark energy. So this had very important insight. This brought us very important insight to our gravitational community. And so this is one example of what has already been done using multi-messenger astronomy. Now, what you can do in future, I'm going to give you one example using what's called neutron star universal relations. So this is the famous mass-radius relation of a neutron star, assuming general relativity and changing equations of state. So one of the biggest uncertainties in nuclear physics is we don't know what is the correct equation of state is in nature for nuclear matter. And depending on which equation of state you pick, you get different prediction for the mass and radius relation. But in principle, you can use this relation to prove gravity. If you know what the correct equation of state is in nature, then you can pick that equation of state, and now you can vary your gravitational theory, and you get different prediction for the mass and the radius relation. This means that if you can measure both mass and radius of a neutron star independently, then you can prove which gravitational theory is preferred or not. But of course, we don't know what is the correct equation state is in nature. So there is a big degeneracy between uncertainties in nuclear physics and also gravitational physics. So to use neutron star systems to prove gravity, then we need to take into account these uncertainties in nuclear physics. And it would be nice if we can somehow project out uncertainties in nuclear physics so that we can concentrate on proving gravitational physics if you want to prove whether GR is correct or not. And that's why some relations called universal relations that do not depend sensitively on which equation of state you pick is quite useful in proving gravitational theory. And one example of such universal relations are the ones that we found among among certain quantities observables of neutron stars I, love, and Q. I stands for moment of inertia, and this tells you how fast an object can spin for a given spin angular momentum, while quadrupole moment here, Q, tells you how much deformation this object obtained away from sphere due to its own spin. And finally, this love stands for what's called tidal love number. This tells you the tidal deformability of an object. If this number is large, that means you can more easily deform an object. So we calculated these I, love, and Q quantities for different equational states, and we plotted one relation. We looked at relations among these two quantities, and this is the result. Different colors corresponds to different equational states, and this assumes general relativity. Unlike the mass radius relation, which depends strongly on which equation state you pick, for these cases, I love Q relations do not depend on which equation state you pick. No matter which equation state you pick, one relation with one equation state will lie on top of each other. And a single parameter along this curve is mass or compactness. And as you increase your mass of a neutron star, then you go from right to left. And this universality is not exact, but we have confirmed that the universality holds to within 1% accuracy. So this could be useful in probing gravity. And let me show you one example by using the I love relation. So this is the I love plane, and this black curve is the GR prediction of the I love relation. And let's assume that in future we measure the moment of inertia to let's say 10% accuracy using double binary pulsar observations from radio telescopes. Then what you can do is you take this plane and then you add this error bar corresponding to this hypothetical measurement of moment of inertia. On the other hand, let's assume that in future we can measure the tidal love number using future gravitational wave observations. And then let's assume that gravitational wave observations allows us to measure this love number to 40% accuracy. Then you can draw in this plane this 40% measurement of the love number, and now you have this error box corresponding to these two measurements. Now, as I said, this black curve is the I love relation, universal relation predicted in general relativity. But if you go away from general relativity, then you typically find a deviation away from this relation. And but any relation has to pass through this error box in order to be consistent with these measurements. So for example, if you pick one theory and you get, let's say, this red relation, then this relation is still allowed because this passes through this error box. Whereas if you pick another theory and it gives you this blue curve, then this is only marginally allowed. And if your theory predicts this green I love relation, then this will be ruled out. So this is how you can use universal relation and future measurements to prove gravity. And as an example, this is the actual I love relation, picking one example non-GR theory that violates parity in the gravity sector. And this theory has one coupling parameter. If you set this coupling parameter to 0, then you recover this GR relation. Here, I picked a coupling parameter such that it is marginally allowed from this hypothetical measurement. And it turned out that this coupling parameter that I picked is million times smaller than the current upper bound coming from solar system experiments, which means that if these observations are realized in future, then you can place million times stronger upper bounds on these types of theory by combining radio observation and also gravitational wave observations. And the reason why we can place such stringent bounds on this kind of theory compared to other observations is because these gravitational theories predict larger deviation if you look at stronger field regime of gravity. So that's why looking for neutron stars are important, and solar system experiments do not place stringent bounds on this type of theory. And since you're combining gravitational wave observation with radio observations, this is one example of multi-messenger gravitational physics that you can do in future. And I didn't prepare for today's talk, but there are also other universal relations, and those universal relations can be used in other directions of physics. For example, you can use some kind of universal relations to probe astrophysics, like a formation scenario of a neutron star inside a binary system. You can also use, for example, the Q-love relation, the relation between quadrupole moment and tidal love number, to extract the neutron star spin better in the gravitational wave data analysis. And there are also other universal relations that can be used to prove nuclear physics better. In other words, to measure tidal love number better in the gravitational wave data analysis. And some of the universal relations even allow us to prove cosmology. So there are many interesting applications of various universal relations to different directions in your physics. And there is some recent review article that I wrote with Nico Younes. So if you're interested, then please take a look at this review article. And now to conclude, maybe I went too fast, but so the take-home message is that from the currently available binary black hole gravitational wave events, these events allow us to place for the first time strong and dynamical field constraints on various gravitational theories. And also, these events allowed us to prove the graviton's dispersion relation deviation away from GR prediction, which is encoded in the propagation stage of the waveform. And that brings us some new insight into a gravitational theory. On the other hand, in future, if you can measure higher order ring down mode of the waveform, then you can test no-hair property of the black hole, and that could be done with advanced LIGO design sensitivity by combining multiple events. And for neutron star binaries, universal relations can be useful in probing various fundamental physics. And I would like to end by listing some open issues. So one important issue is that we don't have yet parameterized non-GR waveform, including the merger and ring down part of the waveform. So to do so, we need to have many binary black hole merger simulations done in theories away from GR so that we build up our knowledge. And then from that information, we try to construct how one can modify the waveform in the merger and ring down part away from GR. And once this is realized, again, we should be able to have stronger bounds on certain theories of gravity. And in my talk, I've only included the leading post-Newtonian correction away from GR. But in some theories, higher post-Newtonian corrections could be important, especially because if you're close to merger, then post-Newtonian approximation breaks down. So these higher order post-Newtonian corrections in non-GR theories could be important. And I don't think there is any spin precessing waveform available in theories other than GR. So this could be important in future if LIGO and Virgo found some highly precessing system in future. And it might be interesting to look for if you can prove other fundamental pillars in GR, like some screening effect in cosmology, and how that would affect the waveform, and whether we can say something about the screening effect from the waveform would be interesting. And in my talk, I've only included the phase correction in the waveform, but if you go away from GR, then amplitude should also be modified. So, and some theories predict that there won't be any phase correction, but there's only amplitude correction. So it's also important to place bounds from amplitude corrections. And since we now have neutron star merger events, it's important to also use this new event to see how much you can place bounds on the PP parameter beta, and from there try to map what we can learn from this new system in terms of general relativity fundamental aspects. And then it's also important to use actual data to, for example, obtain the negative post-Newton corrections, and also to actually prove that stacking multiple events to look for higher order ring down mode actually works or not. And finally, when you stack ring-down signals, the ultimate goal is to see how actually you can measure the frequency and damping time of the high-order ring-down modes. So it's also important to parameter estimation study on the stacked ring-down signal to see how actually you can measure those parameters, and then to see how accurately you can prove a black hole no-hair theorem. So that's all I wanted to say, and thank you very much for your attention.
Going back to the I love Q test of different alternative theories, you were getting a measurement. Yeah, you're getting a measurement of pi and lambda. Presumably, these would have to come from different systems,
yeah.
right? So
yeah.
the system parameters aren't the same.
Right.
So really, you have two entirely different points in this curve.
Right.
How do you reliably combine measurements?
Yeah, that's a very good point. So for this case, what we need to do is, since double binary pulsar system, the primary neutron star inside the binary pulsar system has unique mass, 1.338 solar mass. We need to measure the lab number with the same mass, 1.338 solar mass, to plot a point in this plane, and which you can do by Taylor expanding lab number as a function of mass with some fiducial point. Like you guys have measured lab number at 1.4 solar mass, but you can change the fiducial mass to the mass of the primary neutron star inside the binary pulsar system.
Why did the mass radius relationship for the neutron star and the scalar tensor theory have a pom-pom?
Because in the scalar tensor theories, there are spontaneous scalarizations predicted by some people, and what happens is that once you reach some binding energy in a neutron star system, then you activate a scalar charge in a neutron star, and that creates, so as you increase your mass, at first you don't have any scalarization inside a neutron star, but at some point spontaneous scalarization happens, and this creates a bump, and as you increase the mass further, then you won't have any more scalarization. So the mass radius relation reduces to GR.
Scalar field disappears?
Scalar field is there, but it's just that scalar charge is not activated inside a star.
Why does it go back precisely to the same relation?
I'm not sure in detail. I don't know. Yeah, I don't have an answer right now. I'm sorry.
The resonance needs a precise energy for it to be activated, and even a higher energy is not activating it.
But this is not like Brand-Stick's or something.
No, it's different. It's not Brand-Stick. Yeah. It's a bit more complicated, scalar tensor theory.
So can you go back to this curve, the universal Q curve? So for different equation states, you get zeta 8, previous one.
Previous one, this one?
Yeah. So how much scatter, so you said that there's 1% scatter. How much scatter would you get if you also include magnetic fields up to 10 to the 15 Gauss?
That's, again, very good point. 10 to 15 Gauss, if neutron stars are spinning very slowly, then the quadrupole moment is dominated by the magnetic field effect, so there will be a breakage in this universal relation. And yeah, so if you pick different equation state, you do get different prediction for the I love correlation. But to that to happen, you need to have strongly magnetized neutron star with very slowly rotating system.
If there are more questions for Ken, let's thank him again.
Thank you.